Alright, here we have lecture 2.3, which corresponds to section 3.2 from the textbook. So as previously mentioned, we're focused on chapter 3 of the textbook if you want to follow along in the textbook. We're going to open up by studying graphs. So it turns out we can learn a lot about the characteristics and behavior of a function by studying its graph. For example, we can figure out if the relation in question even is a function simply by studying its graph by utilizing something known as the vertical line test. And the vertical line test states that a set of points are a function if and only if any vertical line intersects the graph at most once. So if a vertical line, any vertical line, touches the graph more than once, it is not a function. Now I really want to stress this if and only if phrase in the vertical line test. In logic, this is called the biconditional. Biconditional is a very powerful logical connective because basically it states if a set of points are a function, then it passes the vertical line test. And if it passes the vertical line test, then it is a function. So it works both ways. That's the bi part of the biconditional. So let's look at some examples. Looking at number 1, you can see no vertical line. I can draw some vertical lines if I want. No vertical line is going to touch this graph more than once. That means it is a function. And what those vertical lines do is they detect if any inputs have multiple outputs. If you recall from the last lecture, we think of x values as our inputs, y values as our outputs. So the domain is the set of all x values. So there's an infinite number of points on this graph, and you can see if there's an infinite number of points, there's an infinite number of x coordinates. So you want to think of, okay, well, all my x coordinates go from where to where? Well, the arrow indicates that this graph is going to go to the left forever. So that means the lowest x value is negative infinity, and the right-hand arrow indicates it's going to go to the right forever, indicating that the highest x value is positive infinity. So that's the domain there. The range is the same concept with y values. So we want to figure out what are all the y values in the graph in between. So the lowest this graph goes is down to -2. You can see if I go down to say -3 or -4, there's nothing going on with the graph down there. The lowest this graph will go is down to y value -2, and it will go up to infinity. So this graph has y values in between -2 and infinity. Now, does it have a y value at -1.5? Yeah, at two places, here and here. Does it have y values at, say, 3? Sure, here and here. So you can see that it will go up towards infinity. Now, the x-intercepts are where it crosses the x-axis. So it crosses the x-axis at -1 and 1. So it's okay to list them just like this, but do not put parentheses around them because then you'd be denoting an ordered pair. And it has a y-intercept at -2. Alright, let's look at this next example. So we can see here that there is a vertical line that hits the graph twice. So that means it is not a function. And maybe you can see now why the vertical line is associated with being a function. This vertical line tells us that this graph maps -1 to some y value and -1 to some different y value. So -1 has two separate outputs. Well, that can't be a function because if you recall from the last lecture, a relation is a function if every input has a single output. So it's not a function, but it still has a domain and range. So all the x values are in between -3 and 3, and here we have brackets because those points are included. And all the y values are in between -2 and 2. It crosses the x-axis at -3, +3, touches the y-axis at -2, +2. Let's look at this third example. So this is also not a function. You can see quite clearly a vertical line will strike it more than once, but it still has a domain. So domain are the set of all x values. So this graph will go to the left forever, and it'll go to the right forever. It's also going down forever and up forever. So all real numbers for the range, and it touches the x-axis at 0, touches the y-axis at -2, 0, and 2. So you can see that this graph has 3 y-intercepts. Alright, last example for this subsection, and we got a portion of my favorite function. This is part of what we know as the sine curve, what you'll see a lot in pre-calculus, and it is a function. Alright, you can see no vertical line is going to hit that multiple times. Now if we look at the domain, all the x values are in between -pi/2 up until 2 pi. So all our x values go from -pi/2 to 2 pi. All of our y values are in between -1 and 1. And then our x-intercepts, we have 3 of them. It crosses the x-axis at -pi/2, pi/2, and 3 pi/2. And it touches the y-axis at 1. And we can actually evaluate function values by studying the graph. So let us go ahead and do that now. So when I look at pi, so pi is right here, I have this point. When I input pi, the graph is at -1. So that tells us f at pi equals -1. So that's why you can always think of your x value as inputs and y values as outputs. For example, the graph has this point at 0, 1. So x, y is kind of like input, output. So when we input 0, the function will output 1. Same thing with pi/2. So pi/2, comma 0, we can view pi/2 as our input. The corresponding output is 0. So at pi/2, the graph is at a y value of 0. And then we can do the reverse of that. For what values of x does f at x equal 1? So if we look at this point, this has a y value of 1, and this point has a y value of 1. There's 2 points that have a y value 1. When we input 0, you get 1, and when you input 2 pi, you get 1. So there are multiple inputs that result in 1. So let's talk about graphing some piecewise functions. And a piecewise function is a function defined in pieces. So what you need to do first is partition your domain, then graph it one piece at a time. So let's look at number 1. So I'm going to call this top piece alpha and this bottom piece Bravo. And when x's are below 4, we output 3. When x's are greater than or equal to 4, we output input -1. So the partition is at 4. So there's my partition. So everything below that dotted line is where I graph A. Let me extend this a little bit. Everything above that dotted line is where I graph Bravo. And let me go over here and label them. So we got alpha, Bravo. So in alpha we're graphing y equals 3. In Bravo we're graphing y equals x minus 1. And we can form two little t-tables. So for alpha, sector alpha, y equals 3, so the x value is always 3, and the y value is always 3, and the x value is, who cares, it's not even mentioned in the equation. So that means it's just going to be a horizontal line at 3. Just like that. And notice it's a strict inequality in alpha, so it will be an open dot at the partition. The reason for that is, note that this is a strict inequality. So what that tells us is we can only graph alpha for x values that are strictly less than 4. So we can get infinitely close to 4, but we can't actually get to 4, thus the open dot. Now if we look at B, sector Bravo, all our x values are 4 and above, like 4, 5, 6, and the y values are x minus 1. So 4 minus 1 is 3, 5 minus 1 is 4, 6 minus 1 is 5, so on and so forth. So there's our dots there. So we'll go ahead and graph those. So we had 4, 3. That's a closed dot because it's a or equal to inequality. We had 5, 4 right there, and we'll go ahead and connect those dots. So here's a piecewise graph where the pieces connect. Now sometimes the pieces don't connect. Let's look at example number 2, and I'll do the same thing. I'll label the top piece alpha and the bottom piece Bravo. We're going to graph alpha for all x values that are below or equal to -2, so that's where alpha goes. And we graph Bravo for everything that's above -2. And we don't really need a t-chart here, because if you don't see an x, this is, alpha is essentially y equals 3, Bravo is y equals -3. Those are just horizontal line segments. If there's no x in there, it's just going to be horizontal. So in alpha, we're graphing up at +3, right there, and it gets a closed dot because of the or equal to inequality. And for Bravo, it's down at -3. It's getting an open dot down at -3. And there's the graph. Notice strict inequality means it's going to be an open dot at the partition. Now, the partition is the only place on a piecewise function you're going to have these open dots, because remember, this is a function, which means it has to pass the vertical line test. So at -2, that vertical line can't hit multiple points. It's only going to intersect with the graph here in alpha up at +3. It will not include the point at -3. So let's look at one last example. So I'll go ahead and label these alpha, Bravo, Charlie, and we'll start partitioning first. So graph alpha is for all x values below -2. So that's going to be everything below -2. So that's alpha, which is y equals -x. And then Bravo is for everything in between -2 and +4. So let me go and draw my partition. So that's where we're going to have Bravo. Now Bravo is y equals 1/2 x. And then Charlie is for all x values greater than or equal to 4. Alright, cool. And we'll just go ahead and graph them one sector at a time. So sector alpha starts at -2 and keeps getting lower and lower. And it's this y equals -x, so all you do is change the sign. Now notice, this one dot will be open. That's because when we go to graph it, it's on the dotted line. So we have to make sure our graph in alpha does not intersect with our graph in Bravo. They cannot intersect. So the only place they could intersect, or I'm sorry, I should not use the word intersect. I should use the word overlap. My apologies. We need to make sure our graph in alpha does not overlap the graph in Bravo. Otherwise, it will fail the vertical line test. So the only place those two graphs may possibly overlap is at the partition, which is represented by this dotted line at -2. So we're going to use an open dot there. That's because we have a strict inequality. Now if we go to graph another dot, it's at -3, 3, -4, 4. All the other dots are just regular points. We only use an open dot at the partition because that's the only place we're worried about it overlapping. Alright, let's go ahead and graph Bravo. So Bravo starts at -2 and stops at 4, so we'll just do the two endpoints. And when we input -2, half of that is -1. When we input 4, we get 2. Now notice, -2, -1. If we look back at the inequality, we can see the or equal to, so this will be a closed point. But at 4, it's a strict inequality. We look back at the original equation, so it'll be open. So at -2, -1, it's closed. At 4, 2, it is open. Oh, -2, -1. Sorry, that point's down here. Make sure I graph it correct. And we'll connect those dots. And there we are with Bravo. Now Charlie, let's go ahead and graph that. So Charlie, sector Charlie starts at 4 and then keeps on going, and it's this input minus 5, so 4 minus 5 is negative 1, 5 minus 5 is 0. And at 4 minus 1, note the or equal to in the inequality, so it will be closed. So 4, negative 1 is closed, then 5, 0, connect the dots, and we're done. And there's our piecewise graph. Alright, that's a wrap for this section. So you're now ready to do the first 2 pages of worksheet 4, but we'll keep pressing forward. Keep up the hard work.